First of all, I want to thank the organizers from SOA who have given me this very nice opportunity to meet up and online and talk about something very close to my heart, tomograms. So today I've just titled this optical and spin tomograms. And here would be a very direct application of the Wasserstein distance, the Kullback-Leibler divergence, and the Bhattacharyya distance to things very physical, because I'll also discuss an experiment as we go along. So basically, the main part of my talk would be on applications of optical tomograms to sensing of photon addition or subtraction from quantized light. And I'll briefly follow that up, if time permits, with comments on spin squeezing in NMR experiments, which might be more relevant to people working on qubits. My references are the following. The optics part of it is largely from a recent paper of ours, where Professor Prashant Panigrahi is also a collaborator. And as he pointed out to me once, this is a nice collaboration between people from two centers of excellence in quantum information, Lakshmi, Bala, Ramanan and Balakrishnan from IIT Madras, and Prashant Panigrahi and Soumya Brata Paul from IIT Madras, and Prashant Panigrahi and Arman, his student. This was recently published in Phys Rev in the letters section. And this paper addresses the several advantages of working with tomograms. As I go along, I will explain what I mean by tomograms and the usefulness of the Wasserstein distance in the context of addition and subtraction of photons to non-classical light. The next paper that I would like to look at is, well, I haven't updated it. It was not just submitted to Optics Letters. It has been accepted for publication in Optics Letters. It is efficiency of tomographic markers and photon addition in deciding photon addition to coherent states of light. And that is where we do a comparison with experiments. So the markers used in this paper are all the three of them: Wasserstein, Kullback-Leibler and Bhattacharyya. That's where we compare with a recently published experiment on photon addition to coherent light and establish the advantages of working with the tomographic approach. So the experimental paper with which the comparisons are made is given here in black. It's a 2024 paper where there was conditional addition of photons to coherent light. So I have learned a lot personally from a set of excellent papers by Professor Vladimir Manko and his collaborators. And I have just put a set of partial references here. And one is an introduction to the tomographic picture of quantum mechanics. And then, of course, optical tomography of photon-added coherent states. And then an estimation of parameters and fidelity of the optical homodyne detection. And this is using a tomographic approach. So tomograms are useful in several disciplines, ranging from medical imaging to physics, because a tomogram is essentially a scan. So as in medicine, if you go for a medical scan, at different angles, an output image of an object is obtained. So each image carries partial information about the object. It's a slice of the full tomogram. And the tomogram comprises such slices, a quorum of such slices. So the full object is to be reconstructed from the tomogram, the set of all slices. Now, in principle, you might need an infinite number of slices, but in our experience, you really need very few slices, the number varying from situation to situation. This is like a medical scan. A priori, you cannot say how many slices you need in a CT scan. It depends on the object that one is trying to scan. But you certainly don't need an infinite number. And it is the same spirit in which we do optical tomography. Of course, there are two major challenges. The first one I've already spoken about. What is the optimal number of slices needed to reconstruct the object? This whole business of going from the tomogram to reconstruction of the quantum state is called quantum state tomography, or QST. A better question, as far as I'm concerned, is can we avoid detailed reconstruction of the object and infer its properties from a finite set of slices of the tomogram? And that's what I mean by a tomographic approach. So here is a flowchart which might communicate to you what exactly we would like to do. So if you start from the top right-hand corner, there is an experiment. Measurements are made, typically homodyne measurements. And these are intensity profiles or intensity distributions or PDFs, depending on the context. You do it at various angles, and a quorum of such intensity profiles is the tomogram. Now, from the tomogram, you could do an inverse read-on transformation and get the Wigner function. That is the relation between a tomogram and a Wigner function. You could use statistical procedures, which in general will be complicated and challenging for continuous variable systems, and get hold of the density matrix. You will be using maximum likelihood estimates in this program. Recently, people have been using a lot of machine learning for reconstructing the density matrix from the tomogram. The problem is this: if the Hilbert space of the system concerned is infinite dimensional, the errors during the reconstruction program would also increase. And I really do not think that people working on qubits or qtrits can get away easy, because with Google and IBM and so on coming up with many qubits, you have a multipartite system with an infinite dimensional Hilbert space. And reconstruction of the quantum state in that case is also going to be a very formidable task. So one can ask a very sensible question. Instead of constructing the density matrix and then compute various properties, in optics, for instance, detecting photon addition and subtraction, quantifying quadrature variances, computing the mean photon number, getting hold of the higher moments and so on from the density matrix. Is there a way of reading off these properties, physically relevant quantities, directly from the tomogram through straightforward, simple calculations, which can readily be done? So if you notice, there is this rectangular outline in blue, and that is the area we concentrate on. From the tomograms, read off directly as much as possible whatever properties of the state that could be of relevance. So if you look at the single mode optical tomogram, it is obtained from multiple measurements, of course. In quantum mechanics, you do a lot of measurements of a set of relevant observables. And you work with the rotated quadrature operators. A and A dagger are the photon destruction and creation operators. For beginning students, since I don't know the kind of audience that is here, if you're a beginning student and you simply don't know any quantum mechanics, but you do know the quantized simple harmonic oscillator, it is the same A and A dagger and the same algebra that you have in the harmonic oscillator problem, except that you take that math and you map it onto photon destruction and creation, reinterpreting A as the photon destruction operator, not the ladder operator of the oscillator, and A dagger as the photon creation operator, not the raising operator in the harmonic oscillator problem. You could make a generalization, and you have rotated quadrature operators, which I have defined there. So the quadrature is defined by this theta. So for each theta, you have a different quadrature, which means you're looking at a different tomographic slice. The tomogram itself is given below, W of x theta comma theta, which is the expectation value of the density matrix in a slice at an angle theta over a continuous set of values of x theta, where x theta itself can be got from x. Look at the last line. The ket x theta theta is e to the I theta a dagger a on ket x. In this context, you will not refer to x as position. You would refer to x as the field quadrature, the x quadrature, because we are now talking about the electromagnetic field, which when quantized gives photons. So if you go back to that definition of W of x theta theta, it is modulus of psi of x theta theta, the whole squared. In other words, you have a probability density function. And in Professor Balakrishnan's talk, he was addressing this whole business of finding distances between such PDFs. I have here a tomogram for you. So the top is the tomogram. Top left is the tomogram corresponding to the zero photon state. The analogous statement in the case of the simple harmonic oscillator would be the ground state of the oscillator. But as I said, A and A dagger are now photon operators, and A dagger A is the photon number operator. So in this tomogram, the top left corner, which I call A, tomogram A, x theta is along the x-axis and theta is along the y-axis. And what you have in color is the PDFs which are stacked for different theta values. When theta is 0, you have the x quadrature. And as you know, x is a continuous complete basis. So for every theta, you have a continuous complete basis given by x theta. Now, if you look at the top picture in the right side, which is denoted by B, that is the tomogram for the 5 photon state. You would see 5 cuts, 5 dark vertical strips in between in that tomogram. Now, this is a sign that you look out for. If you have a 5 photon state, the tomogram will have 5 vertical cuts. The converse is not true. Every tomogram with 5 vertical cuts is not a 5 photon state. And it's worth bearing that in mind. In general, for the n photon state, the tomogram has n vertical dark cuts. The bottom gives you the corresponding Wigner functions after state reconstruction. Now, the information in the tomogram is also carried in the Wigner function. After all information about the state is contained in the tomogram. Now, the Wigner function is a plot with imaginary alpha on the y-axis and real alpha on the x-axis, where alpha is a complex quantity. Real alpha is related to x and imaginary alpha is related to p. Corresponding to the zero photon state, you just have a spot in blue, which is circular. But corresponding to the 5 photon state, you have these concentric rings and you can count 5 rings. So what were vertical cuts in the tomogram have simply translated to rings in the Wigner function. Now, in these cases, the Wigner function is an easy thing to get from the tomogram by doing an inverse radon transformation. In fact, that is true for most single mode states of light. The problem arises when Wigner functions are hard to construct, when state reconstruction becomes a problem, and that is when the tomographic approach becomes useful. So the states of light, the popular states of light, are ideal laser light, for instance, which is coherent light, or CS as I abbreviate it. So it's given as an infinite superposition of photon number states denoted by ket P. The summation over P is from 0 to infinity. So it's a definite superposition, a very precise superposition of the 0 photon state, the 1 photon state, the 2 photon state, and so on. And for beginning students, this coherent light is an eigenstate of the photon destruction operator A with eigenvalue alpha. If you want the physical significance of alpha, mod alpha squared is the mean photon number in the coherent state. So you could add photons to the coherent state. So an m photon added coherent state alpha comma m would be mathematically produced by repeated application of A dagger m times on ket alpha and normalizing the state. And if you want the squeezed vacuum state, that is obtained by applying the squeezing operator on the zero photon state. So you can have photon added and subtracted counterparts of the squeezed vacuum state as well. The field quadrature operators, just to remind ourselves, it's a takeoff from the harmonic oscillator problem, and the field quadrature operators are A plus A dagger by root 2 and A minus A dagger by root 2i, analogous to the X and P operators. Here is the optical tomogram, top left A, the optical tomogram for the coherent light. The Wigner function corresponding to coherent light obtained by an inverse radon transformation on this tomogram is shown in B. And below in C, you have the optical tomogram for a cat state, which is an even coherent state or even cat state, which is a superposition of two coherent states, ket alpha and ket minus alpha. Similarly, the odd coherent state, ket alpha minus ket minus alpha. And these pictures are plotted with mod alpha squared equals 0.5, since that's the, this is, as I said, in the case of laser light, mod alpha squared is the mean photon number. So here we see something interesting. The topmost panel A is the tomogram for the coherent light, which I showed even in the previous slide. But here I've chosen alpha to be 0.7. In general, alpha is complex, but without loss of generality, I'm now going to work with real alpha. B, the middle panel, is alpha comma 1. You see, the addition of one photon has produced a vertical cut. And C, the bottom panel, is alpha comma 2 tomogram, the two photon added coherent state, where you see two vertical cuts. So in general, it can be seen that the tomogram for alpha comma m has m vertical cuts. A tomogram, you can actually choose the theta from 0 to pi, because 0 is the x quadrature, pi by 2 is the p quadrature, and then you get back from pi by 2 to pi, which means from p to x. So you do the full circle if you wish. But we usually show it from 0 to 2 pi or minus pi to pi, because the symmetry properties of the tomogram are very clear if you did this. Once more, there are more pictures to get a feel for this. Top panel, left to right, the single mode optical tomograms for the even coherent state that I spoke about earlier, and its photon added counterparts. B, one photon added counterpart, and C is two photon added counterpart. You can see interesting things now. The zoomed in pictures show us that. So if you look at D, it is the zoomed in version around, around pi by 2, theta equals pi by 2. It's the zoomed in version of A, which is the even coherent states tomogram. The central part is bright. If you move to E, that is the zoomed in version of B, which is the one photon added coherent state. The central part is dark and flanked by two bright vertical lines. And C is the two photon added coherent states tomogram. Its zoomed in version again has the central part which is bright and flanked by alternate bright and darks. We have set alpha equals 1.8. And that keeps ket alpha and ket minus alpha that comprise the ECS sufficiently apart so that the interference fringes, at least in the zoomed in version, are clearly visible. So the intensity shifts are seen at theta equals pi by 2 and 3 pi by 2 when you add photons. So right from the tomogram, if my reference state is ket alpha, I can see that there are addition of photons. Whether it's an odd number of photons that are added or an even number of photons that are added is clear from whether the central fringe around pi by 2 is bright or dark. So this is a very practical situation. If I want to know and quantify the difference between the coherent state and its photon added counterparts, Remember that the tomogram is simply a stack of PDFs. In different quadratures, I can find the Wasserstein distance or the Kullback-Leibler divergence or the Bhattacharyya distance between the two PDFs. And that should quantify for me what happens when you add photons. Now, if you look at this picture, the optical tomogram on the left side, top A, is the squeezed vacuum states tomogram. Add a photon and you see that the central bright fringe becomes dark. Well, it turns out that if you add or subtract a single photon from the squeezed vacuum, analytically you can show that the states are the same. C is when you add two photons, the central bright fringe reappears. D is when you add three photons when it becomes dark and flanked by bright fringes. If you subtract two photons, that is shown in E, the central bright fringe. And if you subtract three photons, that is shown in F. So you see, forget the addition of single photon or subtraction of single photon. In general, if you add or subtract an even number of photons, you get a central bright fringe. If you add or subtract an odd number of photons, you get a central dark fringe. The zoomed in versions close to theta equal to 0, which is where this happens, are shown in the right side. But I have already explained the legend to you. So this is what I explained. Now, if you look at the probability density functions along the X quadrature for the squeezed vacuum, the blue in the top panel is for the squeezed vacuum. For the one photon added counterpart, it is orange. And for the two photon added counterpart, it is green. This parameter xi is complex and it's Re to the I phi. We have set phi to be 0. So the squeezing is along the X quadrature. And R is taken to be 0.38 and 0.52 in the top and the bottom panels. The important point is this: at X is equal to 0, which is the center of the panel of the top PDF panel, for instance, the PDF for xi and the two photon added SVS have a maximum. The blue and the green have a maximum. The orange has a minimum. So this is what is reflected in the shift in the intensity patterns. And you could find the Wasserstein distance between these PDFs or use the other quantifiers, KL divergence or Bhattacharyya. Certain things have to be remembered. I have now given in the left column panels in this figure, A, C, E, and G, an amplified coherent state, G1 of alpha alpha. The G1 of alpha is the amplification gain. So it is simply that its mean photon number has increased now, but it's a coherent state nevertheless. It's an eigenstate of the photon destruction operator. The right column panels are the one photon added coherent state, and this has been done for alpha equals 0.5. In A, in B, it is 1. In C and D, it is 1.5. In E and F, it is 2. So I have merely changed the values of alpha in these panels. Now, as you go down, which means as you increase mod alpha, particularly for mod alpha greater than 1, the vertical cut in the right panel, which means in the alpha comma 1 panels, disappears. And if you come, you said something?
Were you born between 1980?
Sorry? I can't hear you.
No, please go on. Please go on. I think there is some disturbance.
All right, fine. Okay. All right. So as you compare, for instance, G and H, G corresponds to the coherent state and H corresponds to the one photon added coherent state. G is an amplified coherent state and H is the one photon added coherent state. But you see the signature of that coherent state, which is a vertical cut, is missing. Then how do I know the difference between G and H? One is a coherent state, which is a classical state of light. The other is definitely a non-classical state of light. How do I know the difference? The difference can be easily seen by computing the variances straight from the tomogram. This brings us to the subject of classical and quantum amplification. The fidelity between G1 of alpha, which is an amplified coherent state, and alpha comma 1 is maximized for mod alpha greater than 1. This was reported in this experiment. Actually, it is maximized if for an M photon state, Gm of alpha, which is defined below, if that is the way you define Gm of alpha, then the fidelity between Gm of alpha and alpha comma M will be maximized. But we have computed Gm of alpha directly from the tomograms for each alpha and shown that these plots reproduce the experimental plots obtained after state reconstruction. What do I mean by experimental plots? The fidelity plots. And how do I compute the fidelity plots? When the fidelity between two states increases and gets close to 1, the Wasserstein distance, the Kullback-Leibler divergence, and Bhattacharyya distance must decrease. Shall I continue?
Yes, please continue. I don't know, somewhere there comes.
There is some other conversation. Okay, fine.
Yes, some come.
So the point is this: as the fidelity between two states increases, the Wasserstein or the Kullback-Leibler or the Bhattacharyya distances between the two states in any quadrature decreases. So that is how I compute from tomograms properties directly without reconstructing the state and looking for fidelities. So I'm just quoting this formula given by equation 1. This is a lovely paper by Wunsch, and I have given the reference there, tomographic reconstruction of the density operator from its normally ordered moments. It's a 1996 paper in PhysRev A. And here, various moments of a dagger to the Ka to the L expectation. First of all, a dagger to the Ka to the L expectation can be computed this way. You will see that in the integral, the tomogram W of x theta comma theta, the theta is replaced by m pi by k plus L plus 1, which means that I need k plus L plus 1 slices of the tomogram to compute the expectation value of a dagger to the Ka to the L. I can therefore compute the mean photon number directly from the tomogram. I set K and L equal to 1. That's all. I can compute all moments because if I want the variance, I need a dagger squared and a squared. I set K equal to 2 and L equal to 0 and vice versa and so on. So all moments, variances, moments, higher moments, mean photon number, moments of mean photon number, all of them can be computed directly from the tomogram. And as an extra bonus, I can do this quadrature by quadrature to see how exactly things are turning out. So the above are our plots of the amplification gain that I talked about in this context due to addition of photons. You see that the amplification gain for m equals 1, Gm of alpha is given by the green triangles, and for m equal to 2 by the red squares. And this is the way the amplification gain goes. And this has been computed by the experimenters after reconstruction of the state. We have used this experimental data for the range for mod alpha from 0.5 to 2 because that's what the experimenters have used. So although the tomograms, as I showed you, for the amplified state and alpha comma m are visually similar, the variances, say, along the x quadrature computed from these tomograms are different. So I can even do it simply. If I choose the x quadrature, the tomogram gives me the numerical value of modulus of psi of x the whole square, which I can read off at every x. Then all I have to do is this integration, and that gives me the nth moment of x. So if you look here, this is the variance as a function of mod alpha. The horizontal red line is the variance corresponding to the coherent state, Gm of alpha alpha. It has been scaled to 1. Normally the textbooks will tell you that it is 0.5. We have merely scaled it to 1, simply for comparison with the experimental paper. And then you see these 4 black circles, and that is the variance for alpha comma 1 computed from its tomogram. Visually, the two tomograms look the same, but the variances are different. And you can actually see that for mod alpha 1.5 and 2, the two black circles are below the red horizontal line, which means that alpha gamma 1 is squeezed. And therefore, it's a non-classical state. And at mod alpha equal to 1, the variance for the coherent state and for alpha gamma 1 are equal. The black circle lies on the red horizontal line. So this is how I will see the difference between two visually similar tomograms. The Wasserstein distance has already been defined. It's given in equation 2. And capital F of x and g of x are the CDFs corresponding to little f of x and g of x. The Kullback-Leibler distance and the Bhattacharyya distance have already been defined by Professor Balakrishnan, equations 3 and 4. But now it is clear what I plan to do. There are two main comparisons which we can make with the experiment on photon addition to the coherent state. What the experiment did is the following. The fidelities between gm of alpha alpha and alpha comma m versus mod alpha. The plots have been given in the experimental paper. Also, beta opt is the coherent state of optimal amplitude with which alpha comma m has the maximum fidelity, and beta opt is defined here. The experimenters have also obtained the fidelities between beta opt and alpha comma m. Fidelities are obtained only after the state is reconstructed. So the experimenters have gone through the process of reconstructing these states and then looking at the fidelities. But as I said, if fidelity is increased with mod alpha, these quantifiers, W1, DKL and DB, decrease and follow similar trends. Also, if the fidelity increases asymptotically to its maximum value of 1, these markers will asymptotically decrease to 0. And that's exactly, these are the plots from the experiment. The fidelities are increasing, which means that the Wasserstein distance and DKL will decrease. So m equals 1 means addition of 1 photon, m equals 2 means addition of 2 photons. You will see that we are talking about an average value of W1, an average value of DKL, and so on. By average, we mean compute W1 between the two states of concern to us in a given quadrature. Repeat this in different quadratures. Take the average value. Now, you will use as many quadratures as is required for convergence of these average values. In fact, we have only averaged over 5 tomographic slices, and these values of theta have been equally chosen, equally spaced between theta and pi. The trends are very good because you see that the average value of W1 goes down, and similarly DKL. So if you look at the top panel, this is the Wasserstein distance between alpha comma 1 and G1 of alpha alpha. So the green triangles in the top panel, you have got the green triangles and the red squares. For m equals 2, for m equals 1, the green triangles. Okay. Between alpha comma m and beta opt, it is the black circles and the blue asterisks for m equals 2. The take-home lesson is that the trends captured by these average values of these quantifiers agrees perfectly and in fact predicts what the experimenter should see by measuring fidelity after state reconstruction. So for small mod alpha, the plots for DKL are consistent with the experimental result. W1 marginally departs from this, as it is the transportation cost of transforming one PDF to another. For m equal to 1, in the case of beta opt, W1 tends to the distance between ket1, the 1 photon state, and the CS with alpha equals 1. And that's the difference between a state 1 and a shifted Gaussian. Whereas in the case of GM of alpha alpha, it is the difference between state 1 and a non-shifted Gaussian because the coherent state is peaked at 0. The important feature is that there are no crossovers here. W1 does not have the same numerical value for m equals 1 and 2 for a given mod alpha. It simply increases with increase in m. Similarly for DKL and DB. And dB, the Bhattacharyya distance, follows the same trends as dKl. So there is no problem when you add photons to the coherent state at crossover points. That means there is no point where for m equals 1 and m equals 2 addition, these quantifiers have the same numerical value. Such a situation doesn't arise. The m equals 2 plot is higher than the m equals 1 plot always. Now, if you add photons to the squeezed vacuum, this is a case of non-classical light. Both the even coherent state, the cat states, even and odd coherent states, and the squeezed vacuum are examples of non-classical light. In contrast to what I said about the addition of photons to coherent states, in the case of photon addition or subtraction to squeezed light, you find that there are crossovers. Because if you look at the black circles in this plot, W1 between the squeezed vacuum and its photon added or subtracted counterpart, they are the same states. That's the black circles as a function of the squeezing parameter R. Between the squeezed vacuum and its two photon added counterpart, it's given in red triangles. And between the squeezed vacuum and the three photon added counterpart, it's given by green asterisks. You see that there is a crossover between the red and the black at about 0.59, at about 0.45, and between the green and the black at about 0.59. So at these points, one does not know how many photons have been added. But this too is all right, because you just leave the, now the prediction is this, leave these values, go away from the crossover points, and you can definitely see the difference between addition of 1, 2, and 3 photons to the squeezed vacuum. Now, if you look at dKl between the squeezed vacuum and the 1 photon added squeezed vacuum, it is not very sensitive to the squeezing parameter R. The black circles, you see, it's essentially more or less horizontal. That's because of the logarithmic dependence in the definition of dKl itself. It is not sensitive to R. But there is, if you look at the blue, which I will talk about a little later, this is between xi and xi comma 2. The blue goes down, that is fine, but there is a crossover between the black circles and the blue at some value, R approximately 0.3. First of all, the fact that dKl does not show much sensitiveness to R if you add a photon is itself a prediction. It tells you that if your dKl does not change much with R, then you have added 1 photon, or perhaps subtracted 1 photon. But if there is a downward trend in dKl with increase in R, then you have added 2 photons. The fidelity plot, so these are predictions for the fidelity plot. After the entire machinery of state reconstruction, people find the fidelity, but that's going to be predicted right here without doing state reconstruction. So the summary and outlook for this part is addition of photons to the coherent state and addition and subtraction of photons to the squeezed vacuum and the ECS are investigated directly from tomograms circumventing state reconstruction. Visual inspection of the tomograms plus computation of quadrature variances in canonically conjugate quadratures if necessary, directly from tomograms, augmented with mean photon number calculations if necessary, directly from tomograms, suffices to identify the extent of photon addition or subtraction. So tomographic markers play an important role. Their variation with the relevant parameter could be mod alpha in the case of coherent states and photon added states, or the squeezing parameter in the case of squeezed vacuum and its counterparts, can be compared directly with experimentally obtained corresponding fidelity plots. Not surprisingly, therefore, it's good to do machine learning with tomograms, which is what we are attempting to do now. Now, crossover phenomenon seen in the case of non-classical light, such as the SVS and ECS, are there in certain quadratures. The Wasserstein distance, the Bhattacharyya distance, and the Kullback-Leibler divergence are useful tomographic markers in this context. Now, in the case of single mode light, state reconstruction from tomograms is reasonably easy, but it's difficult for multimode states and hybrid systems. So extension of our procedure will be potentially very useful And what we have provided here is the proof of concept of how well the tomographic approach works. In the case of the bipartite tomogram, you can define entanglement indicators tomographically. A bipartite tomogram will have two subsystems, and the angles are given by θ1, θ2, and the corresponding variables by x θ1 and x θ2. It's a straightforward extension of the single mode optical tomogram. The reference is given there by Koronoy and Manco. Again, you can define the Kullback-Leibler divergence and the Bhattacharyya distance easily and readily. If you look at the Kullback-Leibler divergence, for instance, the logarithm has the bipartite tomogram in the numerator and the subsystem tomograms got by tracing out one subsystem or the other in the denominator, the product of subsystem tomograms. Now, this can be a very easy, readily useful entanglement indicator, because if the numerator factorizes in the sense that there is no entanglement, the numerator and the denominator are equal, and you just have log of 1, and DKL is 0. So the entanglement is 0. So DKL and DB also vanish for unentangled states. You can average over the values obtained in different quadratures to get the average value of DKL and DB. Now, these entanglement indicators have been extensively used by us in the context of continuous variable systems. But today, I just want to conclude with some brief comments about qubits. So the experiment that we looked at here, we got data from Professor Mahesh's group in IISER Pune, NMR experiment data, where they had mixed states, and they looked at those mixed state spin tomograms. And of course, now the basis is going to be the spin basis. So you will have the eigenstates of the polymatrices sigma x, sigma y, and sigma z. And you will write the expectation value of the density matrix in these basis states. Therefore, you don't have to deal with a theta, which takes you through infinite slices. There are only a few slices in a spin tomogram. This is an example of a spin tomogram. As you can see, the outcomes are given on the x-axis, 0, 0, 0, 1, 1, 0, and 1, 1. It's a bipartite tomogram. And the measurements are made in the ZZ, ZY, ZX, YZ bases, and so on. And that is put along the y-axis. So this is your qubit tomograms. And our experimental collaborators here are Soham Pal is presently in the University of Cambridge and Pritika in IISER Pune. But and from our own group, we had Sharmila, who is now in the University of Warwick. And the paper is published in 2022 in Journal of Chemical Physics. So 2 experiments to determine the extent of bipartite entanglement in liquid state NMR experiments performed at ambient temperature. The experimenters reconstructed the state from the measurements, used standard entanglement indicators like concurrence, which they got using the density matrix. Dibromofluoromethane molecule ensemble of 10 to the 15 mutually non-interacting molecules dissolved in deuterated acetone and placed inside a superconducting magnet. The subsystems were carbon, hydrogen, and fluorine. Now, what the experimenters looked at was a reduced density matrix corresponding to the mixed state entangled bipartite system, hydrogen and fluorine. The next system that they used was sodium fluorophosphate dissolved in heavy water. The subsystem 1 here is fluorine and the subsystem 2 here is phosphorus. This is an entangled bipartite system. In both systems, the entanglement measures were obtained from the density matrices. And what we got was the following. We retrieved the spin tomograms from the density matrix. We worked backwards actually, computed DKL and DB, and compared with the standard entanglement measures and showed that as functions of scale time, they mirrored the same trends as these measures. So the performance of entanglement indicators, both in qubit systems and in continuous variable systems, and the extent to which these indicators track standard entanglement measures during dynamical evolution, are very sensitive to the precise manner in which the full system is partitioned into subsystems. I believe I have already given you a summary of what I wanted to say. both in the case of optics and in the case of qubit systems. The qubit systems dealt with mixed states, you see, to begin with, whereas in optics we had single mode states, at least as far as this talk is concerned, and therefore they were pure states, known states. I'm now done with the talk and I can take questions.
Thank you, Professor Lakshmi. Now questions, please. Questions?
Can I have one question?
Yes, please.
See, Lakshmi, it's quite remarkable that in the second half, when you checked the concurrence, have you compared for Werner state the behavior of concurrence and this measure?
We have not checked this for the Werner state. The experimenters did not have a Werner state, and we don't have experimental data for the Werner state.
Yeah, but mainly I am interested. Where does this vanish? For example, Werner state basically taught us at some points concurrence goes to 0, right?
That's right.
Between 0 to that temperature or that parameter, you can represent them as, like thermal state kind of thing.
That's right.
Okay.
That's right.
So same thing, does it happen here? Somewhere this breaks down.
Okay. No, three things. I did not mention the rest of the story. There is something called IPR, inverse participation ratio. The inverse participation ratio, yes, it shows those changes. DKL and DB, not so sensitive. There is something called the Pearson coefficient that is not at all sensitive. So as in the case of entanglement measures or monotones, some things, agree and some things don't agree. But it will be definitely reflected in the tomographic measures. Yeah, tomographic indicators.
Yeah, very nice. I'll talk to you later. Yeah, thanks.
So, any other questions, please? So, if there are no more questions, let us thank Professor Lakshmi for her excellent talk. Thank you, madam.
Thank you very much.